Okay, this is the fall 21 exam 4. Here I have a disk of radius 2 meters and moment of inertia of 4 kilogram meters per meter squared. And it is rotating at 3 radians per second, so that is our omega naught. Oh, our radius is 2 meters. And it begins to slow when a force is applied to it. The force is applied is in this figure, and it takes 6 seconds to stop. Alright, so I know it's slowing down, so I know that my alpha is going to be negative something. Let's see, I don't know what the force is, but it looks like I'm going to have to find that. So first of all, what is the angular displacement of the disk during these 6 seconds? So what is theta? Well, I know that theta is equal to omega naught t plus 1/2 alpha t squared, but look, I don't know alpha, and I don't know theta, so I need to figure out what alpha is. But I know that omega equals omega naught plus alpha t. Now something I didn't write up here is that omega is equal to 0 because it's coming to a stop. That omega final is equal to 0. So this is going to be 0 equals 3 plus alpha times t, which is 6 seconds. So alpha then is going to equal to negative 1/2 radians per second squared. So now I can take that and figure out what is my theta. That's going to be omega naught, which is 3, times t, which is 6 seconds, plus 1/2 of negative 1/2. That's my alpha, times 6 squared. 18 minus the quarter of 36 is 9. So that's 9 radians. So that's part A. What work is done to make it stop? Remember, work is equal to a change in energy. So whatever my change in energy is, that's the amount of work. Well, my change in energy is kinetic energy final minus kinetic energy initial. Kinetic energy final is 0. Kinetic energy initial is 1/2 I omega squared. That's omega initial. So that's going to be, my work is going to be negative 1/2. I was given 4. And omega initial was given, that's 3. That's squared, so that's 2 times 9 is negative 18 joules. That's the amount of work that's done to stop it. And I want to know, what is the magnitude of the force? Well, let's see. I know what I and alpha are, so I can figure out what the torque is. Torque is equal to I alpha. That's 4 kilogram meter squared times alpha, which was negative 1/2 radians per second squared. But at this point, you know, the sign is not really relevant. I'm just going to get rid of that sign because I'm not looking for a direction of the force or torque. So that's equal to 2 Newton meters. But that's not what I'm looking for. I'm looking for the force. And as in the figure, see, the force is applied at an angle of 90 degrees. So this is FR sine theta. I can get rid of that theta term because sine of 90 is 1. So my force is equal to torque divided by moment arm. That's going to be 2 Newton meters divided by the length of the moment arm, which is also 2 meters. So it's 1 Newton. All right, let's look at this. Oops, sorry. This is a more typical problem with Newton's second law. First thing I want to do is, what is the net torque? Torque 1 is right here. This is torque 2. Torque 1 is clockwise, so it's going to be negative. Torque 2 is counterclockwise, so it's going to be positive. I can calculate torque 1 is FR sine theta. That's 10 newtons times R, which is 2 meters, times sine of 30. That's going to be 20 times 1/2, or 10 Newton meters. It is negative because it's clockwise, so I'm going to put a negative right there. And then torque 2 is going to be 10 newtons times 2 meters. That's going to be 20 newtons meters. So the sum of all these torques is going to be negative torque 1 plus torque 2. That is negative 10. I see let's get rid of this negative, but we'll carry down that negative from -10. It just denotes that it's clockwise. Plus 20, that's 10 Newton meters. So that's my net torque, and it is a counterclockwise torque. And I want to know what is the magnitude of the angular acceleration. This is B. Well, I know that torque is equal to I times alpha, so alpha is equal to torque divided by I. That's going to be 10 Newton meters. Oh, but I don't know I. But I do know that this is a disk, so I'm going to use I for a cylinder, which is 1/2 mr squared. It's 1/2 of the mass, which is 4 kilograms, times the radius, which is 2 meters squared. That's 2 times 4, 8 kilogram meters squared. So that's my I. So 10 divided by 8. Is that 5/4? 1.3, 1.25, right? Or 1.3 really would be the correct sig figs here. And then what is the rotational energy? I'll do it right here. So to find the rotational energy, we need to know omega. So I can find omega naught plus alpha t. That's going to be 0 plus my new alpha that I found, which is 1.3 times 3 seconds. That's 3.9 radians per second. And then I have to find the kinetic energy. Kinetic energy is equal to 1/2 I omega squared. That's 1/2 of 8, which I've already found, times 3.9 squared. That's 61 joules. All right, let's see. So those are our 3 answers for that one. Now let's do this third one. A bar of length 2 meters. I'm going to go ahead and, while I'm doing this, I'm going to go ahead and find the moment of inertia. This is 1/12 mb squared. That's the mass of the bar, length of the bar. That's 3 times. Oh, that's 1 kilogram meter squared. That's convenient. And then I also have a flywheel. Flywheel is just a disc or a cylinder, so it's going to be I will be 1/2 mr squared. These are both from your table. That's 1/2 of 4 times 2 squared. That's 2 times 4, 8 kilogram meters squared. So those are my 2 moments of inertia. And look, so that's actually part B. To find for part B, let's go ahead and do that. What is the total moment of inertia? It's just going to be the sum of these. So 1 kilogram meter squared, that's for the bar, plus 8 kilogram meters squared. That's for the disk. That's 9 kilogram meters squared. You have to find that en route to the first part anyway. And then what is the new angular speed of the bar? So this thing is rotating at 3 radians per second. And this is not rotating at all. So for part A, I would say L initial equals L final. Your initial momentum is just the bar. So that's going to be I initial omega initial for the bar. And then your final is going to be the sum of those two. I final times omega final. But this I final includes the bar and the wheel, or the flywheel, which is a disc. Okay. So this is 1 kilogram meter squared times 3 radians per second is equal to 9 kilogram meter squared times omega final. So omega final is 3/9, or 0.33 radians per second. So that's the answer for that one. That was a conservation momentum problem. What is the angular velocity of the rotating Earth? Well, that's going to be theta over t. It goes through 2 pi radians in 24 hours. That's what the rotating Earth does. So that's going to be 6 divided by... Oh, I need to convert this to seconds. So in 1 hour, there are 3,600 seconds. So that's going to be 2 pi. I get that 0.00007, 7.2 times 10 to the minus 5. It's in radians per second. 90 degrees, that's this angle, 0 pi over 2, so that's pi over 2. Ferris wheel has a radius of 10 meters. And the speed, sorry, that should be omega, equals 0.5. And mass of 100 kilograms. And I'm looking at the lowest point. So here's my Ferris wheel. I'm at the lowest point. I have a normal force of a weight. My acceleration, which is my centripetal acceleration, is in that direction. So Fn minus Fw is equal to m times a. That is Fn minus the weight, which is 1,000 newtons. That's m times g is equal to 100 kilograms times v squared over r, or omega squared r. I'm going to let a equal omega squared r. Just makes life a little easier here. So Fn equals 1,000 plus 100 times omega, which is 0.5 squared, times the radius, which is 10. What's that? I think that's 1250. Yeah, D is right for number 3. Consider the hammer throw, an event where the athlete swings a 5-kilogram ball. So the mass of this thing is 5 kilograms. And then this distance, I'm told, is 1.5 meters. That's the radius. And it swings at a speed of 2 revolutions per second, or an angular speed of 2 revolutions per second. What is the force exerted on the ball by the athlete? So I want to know, what is this tension? And that tension is equal to my centripetal force. So the tension is going to be equal to m omega squared r. But remember, I need to convert this to radians per second. That's going to be 2 times 2 pi, or 4 pi radians per second. So this is going to be the mass of the ball, which is 5 kilograms, times 4 pi squared, times the radius, which is 1.5, and you get a pretty big force. You get 1,200 newtons for that. Merry-go-round is initially at rest. You apply a torque and cause it to accelerate. At alpha is 2 revolutions per second squared, and then also omega naught is equal to 0 because it's initially at rest. How long does it take the merry-go-round to complete 2 revolutions? Okay, so I want to know what t is. I know that theta equals omega naught t plus 1/2 alpha t squared, and omega naught is 0, so that term goes away. Looks like I know everything else here, and since the omega naught was 0, this is pretty easy to solve. So I'm just going to have 2 equals 1/2 of 2 times t squared. This is my angular displacement. This is my angular acceleration. So t is the square root of 2, which is 1.4. An object is rotating at a constant rate. It slows with an angular acceleration of 2 revolutions per second squared. If it takes 6 seconds to stop, what is the initial angular velocity? Okay, so omega final is equal to 0, and I'm looking for omega naught, and alpha is negative 2 revolutions per second squared, and t is equal to 6 seconds. Okay, so I just say 0 equals omega naught minus 2 times 6, 12 radians per second. What is the angular velocity of the second hand of a clock? Second hand of a clock, that thing goes around once every 60 seconds, and theta is 1 revolution, so 1 divided by 60 is 0.016, 0.017. Chad and Kaisa, hey, that's me, are in a spinning merry-go-round. Chad is on the outside edge, and Kaisa is near the center, which is the larger centripetal acceleration. So Chad is right here, Kaisa is right here, near the center. So she has a smaller r, and he has a bigger r. Well, centripetal acceleration is m omega squared, excuse me, just omega squared r. I use that because they both have the same omega. I wouldn't use this one, v squared over r, because they have different v's. and different r's. So I'm not going to use that. Instead, I'm going to look at this relationship because omega is constant for both of them because they're on a rigid body. And so the one with the larger centripetal acceleration is the one with the bigger radius. Hey, that's me too. Kaisa sits on the outer rim of merry-go-round. Okay, so K is right here, C is right here. Merry-go-round makes one revolution every 2 seconds, so its angular velocity is the same as Kaiser's. Object begins to rotate with a constant angular acceleration. It rotates to an angle theta in a time t. So this is my relationship. If I double t, that's going to quadruple theta. Okay, so here an object is spinning at a constant rate and has a rotational kinetic energy E. Object increases its moment of inertia, and so its angular velocity decreases by a factor of half. So we need to consider its momentum. If it increases its moment of inertia so that this goes down by a factor of a half, this is going to remain constant. That means this has to double. And then I can look at my kinetic energy. I get a factor of a half here and a factor of 2 here. That's going to give me a 2 times a half squared, which is a quarter. That's going to give me a total change in energy of 1/2 the kinetic energy. All right, a hoop of radius 4 meters and mass of 20 kilograms. Rolls at a speed of 2 meters per second. I don't know the total energy. The total energy is equal to the kinetic energy rotational plus translational. That's going to be 1/2 I omega squared plus 1/2 mv squared. So we need some of these quantities. First, we need to know I. For a hoop, that's mr squared. That is 20 times 4 squared. It's 320. And also need to know omega. Omega is equal to V divided by R. It's 2 divided by 4. So it's going to be 1/2 of 320 times 0.5 squared plus 1/2 of 20 times 4 squared. Okay, actually this was a 2 right here. This should be 2. The speed was 2 meters per second, so the answer is 80. Okay, this object can rotate in the plane of the page. Rank the moments of inertia. Okay, well, this one's going to have the smallest moment of inertia, so I can get rid of these two because the radii to all the extremities are their smallest at that point. And this one is going to have the biggest moment of inertia because they have big radii out to all the masses, so I can get rid of that one. So then I just need to distinguish between A and D. Let's see. This one, yeah, this one has more mass at bigger radii than this one does. See, this one has shorter radii to the mass, so D has a bigger moment of inertia than A. Then A. So A is the right answer. Okay, here I want you to find the moment of inertia for this configuration of particles. This is a set of discrete particles. They're at distance 4 meters, and so I is going to be the sum of mr squared. That's 3 times 4 squared plus 3 times 4 squared. 3 times 16 is 48, so it's 96. Here I have a bar
a mass. This is a lot like the free response. It expands and turns into a disk with the same mass and diameter. Let's just calculate the moments of inertia first. That's 1/12 of 6 times 2 squared. 6 times 4 is 24. That's 2 kilogram meter squared. And then here, this is going to be 1/2 mr squared, which is 1/2 of 6 kilograms times 1 meter squared. That's 3 times 1 is 3. So I'm going from 2 kilogram meter squared to 3 kilogram meter squared. And it's like the bar is sort of fanning out into this disk. And now I want to know what is the new rotational. So omega naught here is 3 revolutions per second. So I'd say I omega naught equals I omega final. That's going to be 2 times 3 equals 3 times omega. So it's going to be 2 revolutions per second. Two disks have the same momentum. The radius of disk A is twice the radius of disk B. So here's A, here's B. Both disks have the same mass. The angular speed of disk A is W. What is the angular speed of disk B? So it's something times omega. I say W, I'm sorry, omega. So here, how do the moments of inertia compare? Well, if this is I, this is going to be 1/4 I. Because remember, I is 1/2 mr squared for a disk. And so if I have half the radius, I'm going to have 1/4 the moment of inertia. So if I have 1/4 the moment of inertia, I'm going to have 4 times the speed. So number 16 is A. What happens when a spinning moves her arms out away from her body? Well, this is going to happen and none of the others. You might have been inclined to put this one, but actually this stays the same. So it's just D. Moment of inertia for this bar is 4 kilogram meter second squared. Was the angular acceleration? Oh gosh, okay, so we've already had this one or something similar to it. So first let's find their net torque. I'll call this torque 1, this torque 2. This one is counterclockwise. Oh, so is this one. So it's going to be 20 times 5 times sine of 30 plus 10 times 5. So 150 plus 50, that's 100 Newton meters. And then I need to find I. That's going to be, oh, no, I don't need to find it because it's actually already given, so it's equal to 4. And then I can find alpha. So it's going to be D is the right answer for 18. Now I want to rank these torques. These two have the same. Oh, so that tells me the answer right there. And then B is next, and then A. And then, of course, this is my favorite course. All right, tough test, y'all. Have a good day.